Dear students, in the last lecture, we have discussed about the propagation of plane waves in a lossy medium, and we have discussed some of the examples. In this lecture, I'll be covering the propagation of plane waves in a lossy medium, which is basically ionized gas medium, and also I will discuss about what you mean by the group velocity when you talk about the propagation of electromagnetic waves in a lossy medium. So, in Earth atmosphere, in an altitude about 50 kilometers to 500 kilometers, it is usually called as ionosphere because it contains a lot of ions, negatively charged electrons, and also positively charged ion cores. And these are created by the created when the UV rays enter into the atmosphere and they collide with the atoms and molecules in that particular region of the atmosphere. Okay. Now, so when it collides with atoms or molecules, it will create free electrons as well as positively charged ion cores. And these positively charged ion cores are heavier when compared to the free electrons, and the densities of these charges are almost equal, and you can call it as a plasma medium. Okay. And since the positive ion cores are heavy, they can treated as relatively in the rest state, and free electrons, I mean the electrons are free to move in the region. Okay, so you can treat it as a free electron gas. Okay. When an electromagnetic wave propagate in such a medium, what is happening is that you consider an electron of charge E minus E and mass m. Suppose there is a electromagnetic wave with electric field which is time harmonic, is propagating in the x direction at an angular frequency omega. Okay, and the electron will feel a force due to the electric field of the electromagnetic wave, and which is given by the charge times the electric field, which is given by this expression. Okay, now so this force can be written in terms of the Newton's law, which is m d square x by dt square. And if you use the phasor notation instead of this vector, the position x, you can introduce a phasor for the displacement of the electron. And in the phasor notation, there is a second derivative going on, so second derivative will give rise to a factor of I omega raised to 2, which is minus omega square factor will come out, so it will finally becomes of this expression. Now you should be careful that in the next line, in this expression, x and e are in the phasor notation. Okay, so the displacement of the electron is given by E by m omega square E. Now you can define what is the electric dipole moment, corresponding dipole moment, which is charge times the displacement. Okay, which is given by minus E in E times x. Okay, and if you talk about the polarization happening, so what is happening, overall picture is that you have an electromagnetic field entering into the ionosphere, and it will polarize the electrons in the direction of the electric field. So there will be a charge separation. Okay, positively charged ion cores and negatively charged electrons will be separated by small distance. So there will be some dipole moment creating for individual atoms or molecules. And if you talk about the dipole moment per unit volume, it is called the polarization. Okay, now suppose that there are n electrons per unit volume. Basically this n electrons will be created from the n atoms, suppose. Then the polarization is given by number, so this is the capital N will be the electron density or number of free electrons per unit volume. Okay, that electron density into dipole moment for individual dipole will give you the polarization. So you can substitute x here from this expression and simplify this to obtain this expression of polarization. Okay, here also the polarization is in the phasor notation. Okay, now when you have polarization, you can define the electric displacement as epsilon 0 E plus P. All these quantities will be written in the phasor notation. So I will not be repeating it again and again. So you please be careful with the notations. Okay. Now epsilon 0 E, you can substitute the polarization expression here, and you can take out the electric field outside, and you will arrive at this expression. And you know, in a linear medium, you can write down electric displacement as epsilon times E. So this epsilon, we call it as epsilon P. Okay, which we write as epsilon 0 1 minus omega square P by omega square, where omega P is the plasma angular frequency of the medium, which you can taken as this Ne square by m epsilon 0. Okay, so while substituting in this here, you can define one quantity which is plasma angular frequency. In terms of the angular frequency, you can write down the electric displacement like this, and this epsilon up to this term is called the permittivity of the ionized medium, which is given by this expression. And in terms of the plasma angular frequency and linear frequency, you can write it like this. Okay, so this Fp is called the plasma frequency of the medium. Okay, so here there is a particular situation that when F is equal to Fp, what happens when F equal to Fp? Your plasma medium will be having a permittivity of 0, because 1 minus 1 will come and it will become 0. So even if the electric field is not 0, the permittivity of the medium can be 0, and it will lead to plasma oscillations. Okay, now in this type of medium, the propagation constant gamma, you can return it as you know, this expression j omega root of mu epsilon. Instead of epsilon, we substitute this expression and simplify it as like this. Okay, so and the impedance, you can write it like this: epsilon 0, where mu 0 by epsilon 0 is the intrinsic impedance of the vacuum medium. Okay, and this its value is about this constant is about 120 pi, which I forgot to mention in our lecture. Okay, so this is approximate value, but it will be useful for doing problems. Okay, now so you have propagation constant and eta p. This you can easily obtain because we have done it for 2-3 times how to obtain these relations. Okay, now let me conclude here. What happens when frequency is less than the Fp? Okay, plasma frequency. When F is less than Fp, you know, this propagation constant, this term will be a completely real term. Okay, because F less than, sorry, I'll repeat it. When F is less than Fp, this term will be greater than 1. So this will give you complex value. Okay, so there will be a j value here and there is a j value here. So when you multiply two purely imaginary numbers, you will get a purely real number. Okay, so this means gamma is purely real, and if gamma is real, you know, gamma is usually in general complex, which is having a real part and a imaginary part, alpha plus I beta, and this complex part will determine the propagation and alpha part will give you the attenuation. Since we don't have any complex part here, it is completely real, so you have only alpha part. So you can say that the wave will attenuate without propagation. Wave will quickly attenuate, it will not propagate. Okay, and in this case the impedance eta p will be purely imaginary, because this is imaginary and this is real. So eta p will be imaginary. It is called a reactive load with no transmission of power. So the limiting case Fp is called the cutoff frequency of the medium. Okay, so if the frequency is less than the cutoff frequency, there will not be any wave propagation. Okay, so suppose frequency is greater than fp, then you can say that gamma is purely imaginary. It is having only imaginary part. There is no attenuation part. The real part it is not there. So you can say that the wave propagate unattenuated in the plasma. Okay, so this is all about the propagation of electromagnetic plane waves in the ionized gas medium. Now, next we look at the term when you talk about the propagation, wave propagation in a lossy medium. An important parameter here to discuss is the group velocity. Okay, and we know how to define the phase velocity of the wave. When you talk about the propagation of single frequency plane wave, just when you divide the angular frequency by propagation constant beta, you will get the phase velocity, and it is the velocity of propagation of an eq phase wavefront, that you know, and we have discussed this previously, and we have calculated the phase constant and the phase velocity for different cases in the lossy medium. Okay, sorry, in the lossless medium. Now, so the phase constant for a lossless medium is proportional to omega, angular frequency. Okay, but this is not true in general. Okay, since the phase constant is linearly proportional to omega in the case of lossless medium, the phase constant phase velocity will be also constant. It is depends only on the permeability and permittivity of the medium. But in many cases the phase constant is not linearly proportional to omega. And what are the consequences of this this fact, the fact that the phase constant is not linearly proportional to omega? So the situation here will occur in case of lossy medium and transmission lines, waveguides, etc. In this kind of mediums, the generally phase constant is not proportional to omega, and in such cases the different frequency component, if there are more than one frequency, not merely one frequency component, if there are many frequency components, then all these different frequency components will travel with the different phase velocities. So the impact of this is evident when you have a signal. Okay, usually a signal will be having different frequency component. You know how to separate the frequency components of a signal. Okay, how do you do that? You can use the Fourier series. Okay, and you know a periodic function can be written as a sum of the simple harmonic terms. Okay, according to Fourier theorem. So there will be different frequency components in the signal. Okay, and suppose a signal is propagating in the plasma medium, different frequency component will travel with the different phase velocities. Okay, so what happens is, if you have a signal and which is of a Gaussian shape or some definite shape, as it propagates, the shape of the packet, okay, I would say it as a wave packet, the shape of the wave packet will be distorted. So such a signal distortion caused by the dependence of phase velocity on frequency is called distortion. Okay, so immediate example you can say is a lossy medium is a dispersive medium. Okay, like lossy medium like plasma, or ionized gas medium is a dispersive medium. So in such cases, since different frequency components have different phase velocities, we can define a common velocity parameter which is called group velocity. So group velocity is the velocity of envelope of the wave packet. Okay, it is an envelope. Here you can see there is a signal and individual waves will superimpose to form a wave packet, and you can see there is an envelope which is going on. So this is the outer portion of the signal. Okay, and the velocity of this envelope is called a group velocity, and velocity of the individual waves in the packet is called a phase velocity. Okay, Now, in order to find an expression for the group velocity, we consider a simplest example of superposition of two wave packets, which is having a frequency omega 0 plus delta omega, and another we consider the wave packet created by the two different frequencies of the waves, or superposition of two waves, one of which is having frequency omega 0 plus delta omega, and another one which is having omega 0 minus delta omega. So there is a very small difference between the two frequency of two waves, okay, and the difference is given by delta omega. And when they superimpose, and since they have different angular frequency, their phase constant are also different. First one will be having a phase constant of beta 0 plus delta beta, and the second one is having a phase constant of beta 0 minus delta beta, okay. And when they superimpose, so the first wave I can write it like this. So here it is the instantaneous value of the electric field, okay. So you have an amplitude, and I'm taking cosine as a reference. So the phase term will be having omega 0 plus delta omega t minus beta 0 plus delta beta is it. Similarly for the second wave, and you can simplify this. You can take out E0 outside and simplify this expression using the trigonometric relations and arrive at this expression, okay. And if you look at this expression, it is having an amplitude 2E0, and this term is like the usual phase term, okay. This term is a phase term, and even though the amplitude is 2E0, there is an additional cosine variation to the amplitude, okay. So since delta is very much less than omega 0, you can actually call this as a rapidly oscillating wave having an angular frequency omega 0 and amplitude that varies slowly with the angular frequency omega. So this amplitude varies slowly with the angular frequency omega, okay. Now if you look at the wave inside the envelope propagates with some velocity, or you can write down how to find out the phase velocity. You look at the points where the phase constant is phase term is constant. So you take omega 0 t minus beta 0 z equal to constant, and from which you find out dz by dt, the velocity, phase velocity, that is omega 0 by beta 0. So this we know the expression for the phase velocity. And how do you calculate the velocity of the envelope? If you want to calculate the velocity of the envelope is modified by this term, okay. So the amplitude varies slowly with the angular frequency delta omega. So you have to look at the term which is constant for the envelope, okay. So you have to fix this value constant, so that will give you this expression, and from which you can calculate the velocity of the envelope by dz by dt, that is delta omega by delta beta, okay. And in the limit delta omega tends to 0, you can convert this into differentials, okay, and you can write down it as d omega by dt, d omega by d beta, or 1 by d beta by d omega. So this is an expression for the group velocity, okay. And this expression for the group velocity is valid even if there are many waves are superimposing, okay. Now we look at the group velocity of the waves propagating in a ionized medium, and for that I am taking the expression for the phase constant here for the ionized medium. This we have discussed already, and we look at the critical case where the cutoff angular frequency equal to cutoff angular frequency omega p. At this point you know beta is 0, and for omega greater than omega p, wave propagation is possible, and we have discussed this when the frequency is less than the cutoff frequency, there is no propagation. Wave will be attenuated fastly. And if omega is greater than omega p, there will be wave propagation. And the phase velocity is given by omega by beta. So from this expression, we can find out this omega by beta as c by omega p by square root of 1 minus omega p by omega whole square. And from this expression, you can also find out d 1 by d beta by d omega, and from this you can calculate the group velocity as c into 1 minus omega p by square root of 1 minus omega p by omega whole square. Okay, and if you carefully look at this expression, this term can have value which is less than 1, I mean the denominator. So that will give you omega p is always greater than or equal to c. It can be greater than the velocity of the light, but group velocity is always less than or equal to c from this expression. Okay, and you can also derive this expression up into ug is always c square of the velocity of light in the vacuum. Now can also derive one general relationship connecting the group velocity and phase velocity. So you start with a d beta by d omega, and you substitute for beta omega by up, and you differentiate it, and so you can play around and find out this expression for the group velocity and how it is connected to the phase velocity. Okay, so according to this relation, you can have 3 different cases, 3 different possibilities when the medium is non-dispersive medium. Non-dispersive in the sense the phase velocity does not depend on the omega and beta, or you can also say that the propagation constant beta is a linear function of omega. Then the derivative of up phase velocity with respect to angular frequency will be 0. Okay, so in that case this term will be 0, so ug will be equal to up. And in the case of normal dispersion, in the sense up decreasing with omega. Okay, as the angular frequency increases, up is decreasing, that is called the normal dispersion. So this term will be less than 1. Okay, so this term will be less than 1, so ug will be less than 1, less than up according to this expression. And in the case of anomalous dispersion, so this is an unusual case, but it can also occur. So up increasing with the omega, the phase velocity increases with omega. So in that case this term is greater than 0, and this term will be greater than 0. It will be a positive term, so ug will be greater than up. Okay, so these are the different cases of medium according to this expression for relation connecting group velocity and phase velocity. Hope you understood the video. Thank you.